Hi guys, Shouvik here. Welcome back to our YouTube channel. So today we will solve another question from Leetcode. So let's get started. Yes. So today we have count good numbers. So first we will try to understand the problem statement. Then we will go to intuitions building, and post that we will go to the code iterations. And after that, TC and SC time and space complexity analysis. Cool. Yeah. So a digit string is good if the digits 0 indexed at even indices are even and the digits at odd indices are prime. So prime are 2, 3, 5, 7. So I think the first line is quite clear to you guys. So they will giving you a digit string. And they might not giving you a digit string, but the definitions of a good string, a definition of a good string is it should be a digit string and its even positions, even indices. So 0 starting from index 0, the even indices have even digits, and odd indices would have prime numbers. So what are the prime numbers of single digits 2, 3, 5, 7? So for odd indices it should have prime numbers. For example, 2, 5, 8, 2 is good because digit 2 and 8 at even positions, because 0 is at even positions and 0, 1, 2, and this is index 2, and even positions that is of index 2 has also even number, that is 8. At even positions are even, and the digits 5 and 2, this 5, and I guess you guys are able to highlight, able to see the highlight which I am just giving here. And these two, these are odd positions because that is 0, 1, 2, 3. So that is of index 1 and that is of index 3 has value of 5 and 2. Both of them are prime. So if that conditions is valid, then we will say this 2582 is a good string. However, 3, 2, 4, 5 is not, because 3 is at even index, but it is not even. So here you can see this index 0 has 3, but the index is even index, and on even index we got a odd value, that is violating the rule. So now, given an integer n, return the total number of good digit strings of length n. Since the answer may be large, return it in 10 raised to the power 9 plus 7 in the modulo. So a digit string is string consisting of 0 through 9. That is very obvious. That may contain leading 0. So if you guys following me, like if you are following my every video, so on yesterday we solved a question where it has the leading 0 is not allowed, but as it is a digit string, they are allowing the leading 0. They are allowing the leading 0 because it is a digit string. But it is if it is a number, then for number, if we have a leading zeros, then that is not going to altogether not a length in. The length is going to be string. So but for string it is allowed. We should have some leading 0 also. So here you can see on this test cases, they are basically looking for all one length good string, all one length good string. So here you can see they give the example of 0, 2, 4, 5, 6, 8. So all of the numbers, because we have only single digit. So the 0 index should have even numbers. So how many even numbers we have of single digits? It's 5. So that's the reason the answer is 5. And for 4 you can write it's 400. It is quite difficult to write, and for 50 it is these things like that many numbers. So I guess the question is very straightforward, and you can see the constant is as big as 10 raised to the power 15. So the answer can have a positions of 15 digits at max, right? So if you followed us on, if you like basically gone through the last video which we just solved, that is a hard difficulty question, so where we have detailed discussions of permutations combinations topic. So this question is just a permutations combination. If you are if your permutations combinations fundamentals are very strong, then you just able to solve it like a few minutes only. So yeah, but I will give you the proper intuitions of what actually we should have to be looking for. Yeah. So how actually you have to think for such question. So let's suppose I am considering for n equals to 5. So for n equals to 5, I have total of 5 places. I have total of 5 digits where I have to put some digit string, so that it becomes good. So for if I can write the index in terms of even odd. So first index is even, next index is odd, even, like this way. So if you can you create a generic formula? If you have n equals to 5, how many odd indices digits you have? How many odd indices altogether we have it, and how many even indices we have it? How many odd indices we have it? How many even indices we have it? So can I say my odd indices, or whatever the naming I am following here, odd count or the odd indices we have it. So how many odd count indices we have? So can I write it? It's of n by 2. It's standard divisions like integer divisions n by 2. And what is then even? Even count indices is nothing but n minus odd count, nothing but n minus odd count. Can I write it? Yes, obviously. So for 5, the odd count is coming as 2, the even count is coming as 3, right? Because we have 1, 2 odd indices and register n minus odd count is nothing but this. So that many even count indices. Agree. If my n is even, like 4, 1, 2, 3, 4, then also if you put how many odd count is 1, 2, and n minus 2, even count is this. So this formula is generic. So this formula will work for both n is even or n is odd. This formula will work. So we are able to define a formula where when we have 2, 3, 4, 5, let's take it 5. So for how many odd indices we have it, how many even indices we have it. So we know this indices is going to be even, this indices is going to be even, this indices is going to be even, and this indices is going to be odd. And for odd index, we will put prime numbers. And for even index, we will put even numbers. Even digits of single. So very brutally. Can you say how many single digits even number? Because it's quite explanatory. For see, we have options to put a single digit. How many single digits even number we have it? How many we have it? 0, 2, 4, 6, and 8. This 5. How many then? 5. How many prime numbers single digit we have it? How many prime numbers of single digit we have it? 2, 3, 5, and 7. That is of 4. So for every even index, how many options we have? So for if I can again write it 1, 2, 3. So this video is going to be very quick. I will be just so this question I personally feels on the side of like not that much difficulty that we solved on yesterday. If you just able to understand, if you are just able to find out the trick, how many options you altogether have it for even positions and how many options you have it for your odd positions, then that's it. After that is just going to be a simple mathematics. So for even positions, I know we have 5 options. So for every even we have 5 options. What are those? 0, 2, 4, 5, 6. 0, 2, 4, 5, 6. For every even I have 5 options. And for every odd I have 4 options. Right? Agree? So what else then? What else, guys? So how many good strings then? How many good strings as per your permutations combinations logic? So for even index we have every even index we have 5 options. For every odd index we have 4 options. Then how many strings? Just do multiplications every of them. So that many options we have. So that is nothing but your answer. So that you have to return. Exactly, that's it. So now why we have find out how many even indexes we have. So let's suppose we have even count here is 3 and our odd count here is 2, right? So how many 5 occurrence? So how many 5 occurrence? How many 5 multiplication is 3 5s for every events for every even index we have 5 options. How many even indexes we have? That's it. And for odd index, how many odd we have? 2. Then how many 4s we will multiply? 2 4s we will multiply. That is our answer. So if I can make it a little bit more generic, so it can be write as 5 raised to the power even count, because 5 plus is going to be 5 raised to the power 3, and 4 raised to the power 2. So 5 raised to the power even count into 4 raised to the power odd count. That is the formula. And for everything you have to do under modulo. You have to. So that is our formula. So that is the formula we just have to apply, and that is your answer. 5 raised to the power even count, 4 raised to the power odd count, multiplications of both, because we can process even indices independently, odd indexes independently. So that is independent processing of even indices, that is independent processing of odd indexes, and multiplication of those. As simple as that. Now here you can see that is of, so this 5 raised to the power even count into 4 raised to the power odd count. So this is going to be some kind of like PLE you will get, because your even count as big as how much? Even count is, if your total size is 15, then even count as big as 10, 15 by 2 it's still, so it can grow as big as 8. and this can grow as big as 7. This can grow as big as 7. So you can multiply 5 8 times and 4 7 times, and then multiplication of both is going to generate your answer. But here but if you can submit, I guess I have also tried with the same, but this is going to give you a TLE. So I think the constraints are very strict. They are going to looking for this multiplication, like multiplication of 5 8 in logarithmic time, multiplication of 5 8 in logarithmic time, not a linear time. We can't do a 8 length loop also to multiply 5 or 7 length even count loop also. That is also not allowed. The constraint is as strict as that. So for that there is a concept known as binary exponentials. I think most of you guys already aware of, but if you don't know, then I will give you a high level gist of that. But most of the modern programming language has inbuilt support of binary exponentials. If you can write it like pow of like on Python, if you can, there is a pow functions, pow of 5 comma even count and modulo. If you can pass, and modulo is for your case is 10 raised to the power 9, then it will completely work. And for even also for odd also, if you can write it 4 into odd count of mod, then also it will going to work. And after that you can take a modulo of entire things, modulo of entire answer, and you can store it to your answer, and after that you can return your answer. So this is completely work, and this is altogether be 100% faster than all submissions. But if you want to understand how binary exponentiations is going to be work, then I can give you a high level overview, because for this particular question is altogether maybe interviewer looking for binary exponentials. Otherwise, like, I know that identifying the formula is kind of a tricky, but after that, like, the binary exponentiations is on implementation part, maybe the interviewer is basically looking for. So I will give you a high level, but if you want me to make a separate video of binary exponentiations, then I will be happy to do so. So binary exponentiations is something like work as a, if you have 4 raised to the power 4, then you can write it as a 4 raised to the power 2, and this power is going to be divided by 2, because both are going to be cancelled. So altogether we are not making any change. So 4 raised to the power 4 can be written as 4 squared, that means 16 to the power square, 16 square. Agree. So 4 raised to the power 4, we can write it as a 16 square. So here you can see we have to loop these things. If we have to do 4 raised to the power 4 in linear, so we have to run a loop till the power times. But here you can see the power is going to be divide. And now what we have, 16 raised to the power 2. Again we will do the same things. We will take 1 2 inside, and we will make a 2 by 2. Again it is same. So this 16 raised to the power square can be written as 256. 16 square is 256 into raised to the power 1. 256 raised to the power 1, we can write it. And finally, when we have a odd length power, we can't do our divisions. So on that case, whatever the a factor is given to us, we will take from that. So I think now 4 raised to the power 4 is nothing but 256 only, and 16 into 16, we can write it as a 16 into 16, and 16 into 16 is 256. So you can get your answer, right? How many iterations we have to do? We have to iterate 1 times and 2 times. So 1 is like 16 square. This times we just by divide by 2, we are able to land on this, and after that these operations also we are able to land on this 256 raised to the power 1. 256 raised to the power 1. Exactly correct. So by only divide operations, we are able to land to the answer. So if you can take some more bigger case like 4 raised to the power 8, you can write it as a 4 square, and whatever the outside, do a 8 by 2. So what it is nothing but 16 raised to the power 4. So your power you can see from 8, it is just divide by 4. It is going to divide by 2 every time. So that's the reason it is a binary exponentiation will work in a logarithmic factor. Again, you have a even power. So here it can be written as 16 square by 4 by 2. 16 square into 4 by 2. So this is nothing but 256 raised to the power 2. Again 256, I will take a square inside, and I will do a whatever the power by 2. Then 256 square, I can consider this is nothing but x. I don't have a calci in hand, so I can write it x to the power 1. So finally how many divisions you do? You jump from this to directly this state 1, and from this you jump on this state 2, and from this state you jump on this state 3. So for 8 you did how many? 3 loopings. 3 loopings. For 4, you did 2 loopings. For 8, you did 3 loopings. So if you can write it in log of 8 base 2, right? How you can write it? Log of 2 cube log 2 base 2. This is going to give you 1, right? And 3 is coming to be in front. If you know logarithmic, 3 into 1. So this is going to be 3. So what is the loop iterations count? Is 3 times you will loop it. 3 times you will loop it. So that's the beauty of binary exponentials. You will not iterate 8 times if you have your, as we discussed, right? Your even count as big as 8, because it's 15 by 2, right? And you for even it can be one extra for odd length size. For odd, if your n is odd, because our n is 15, then our even count is 8 and our even count is 8 and our odd count is 7. 8 plus 7 is 15. So for 8, if so they are not allowing to iterate to 8 times also. They are looking for 3 times iterations, maybe they have maximum allowed. So how we can do? We have solved it with binary exponentials. We will not iterate 8 times, 5 into 5 into 5 into 5 like 8 times. So we will do binary exponentiations. You can use the POW formula, but I have written my binary exponentiation template. I have it that I am following from my competitive programming. I have submitted with binary exponentiations my own template, and that is also going to be 100% faster than all the submissions of the Leetcode. So actually POW functions internally doing that same. I gave you a high level gist of how it is working. Now I will give you the template overview of the code level type div also. But on high level, the exact same things I have written. But if you need a separate video of binary exponentiation, please make a comment. I will be happy to do so. I will make it on a separate topics altogether. Yeah, so that's all about this particular question, intuitions building. Now let's go to the code iterations we have to do. So I have taken modulo what they have asked for, 10 raised to the power 9 plus 7. Odd count is n by 2. Even count is n minus odd count. As simple as that. And our answer should be helper. I will explain. On helper I am using binary exponentiation. Helper is 4 raised to the power odd count, 5 raised to the power even count, and take off. Everything should be under modulo. 4 raised to the power odd count, 5 raised to the power even count. Same formula. If I man, do you have write the same formula? 5 raised to power 5 raised to the power even count, 4 raised to the power odd count, exactly same things, and inside of multiplication of both, same formula. Helper of 4 raised to the power odd count, 5 raised to the power even count, multiplication of both, and this is also should be under modulo. This also should be under modulo, exact same things. Now on helper, I have written the exact my own template of binary exponentiation. No fancy things I did here. So I have two results to be 1. And while my b, that is the POW, like 4 raised to the power 8, 5 raised to the power 8. So b is the 8 factor. How many times we have to multiply? So if my b is odd, if my b is going to be odd, then I have to decrease 1a. To decrease 1a, because I know a is going to multiply it by b times, and b is going to be odd, then if I can reduce 1a from it, then I think we should be good. Then on that case, then again my b is going to be odd. Again my b is going to be even, because somehow b is now odd. So I have to done a results of a. I have just reduced 1a and I have considered its value to my result by multiplying it to a, right? And as everything should be done under the modulo, I did a result modulo of mod, exact same things. And after that I have multiplied by a to a, because you remember, right? Here what we have done. So for 4 squared, we have write it whatever the value we have when we are doing binary exponentiation. This factor is going to be squared out. So this number is going to multiply whatever the value it have as. So here you can see on this example, when we have 4 is going to become 16. So 4 into 4. So whatever the a value we have it, multiply it itself. So here you can see, like when we have 16 raised to the power 4, what we did, 16 squared into 4 by 2. So 16 is going to be multiplied by itself, and power is going to be by 2. So man, did you do exact same things? Yes sir, I have did exact same things. A is going to be multiplied with itself, and as we have to do everything under modulo, so these lines to you anyhow have to write, because everything should be under modulo. They have asked for this particular question, and B is going to be by 2. And I guess if you are following this is also your known things. If how you can do a by 2, by like if you right shift a number to 1 places, then that is nothing but the divide by 2. If you on bitwise, if you know bitwise right shift operator, then that is a cake for you. So here you can write it also, if you are not able to understand, you can write it b double divided by 2. So that is also exact same things. If you do b right shift by 1, that is also a divide of that particular number. Yeah, and finally we are returning the results. So exact my own template of binary exponentiation. Extra lines, this is because we have to do everything in under modulo. This is extra lines. But if you not able to understand the help part, then please make a comment. I will be happy to make a separate video of binary exponentiations, right? So that's all about this particular question. It is as simple as that, guys. And now quickly we can discuss the time complexity. So on time complexity, we are doing only of binary exponentiations of these factors only, and we just, so it is going to be taking a big O of 3. big of 3, because big of 3 plus, let's suppose, big of 2 as worst case. It is all together as constant only, big of 5 kind of complexity. Yes, that's it. That is the exact time complexity. This things is happening in logarithmic factor. So for 15, we have log of 8 base 2 and log of 7 base 2. 7 base 2 I can consider it is kind of 2 point something, 2.5. So I can consider this, or I can consider it as a 3 also. And this you can say as a big O of 6 kind of complexity. It is as constant. It is as constant. So my submissions is like to 0 milliseconds, but yeah, like it is 100% faster. So I guess you guys also correlate how it is that much fast. And for space perspective, do you guys feel we are using any extra space? We are playing only variables. Yes. On space, we are using constant space. So everything is constant. Yes, guys. So that is the most optimal time and space complexity for this particular question. And if you guys are able to understand till this point, I guess you guys know what you have to do. So please do subscribe to our channel. Please share the videos to your friend circles who are also preparing for top product list company and also doing the brush ups of their DSS skills. Please share the videos to them, and please turn on the notifications so that when we are going to be live to our next video. So that's it for this video, and let's meet tomorrow with another beautiful video. Bye guys. Bye.